Hello everybody, Dr. Bianchi here, and in this lecture video, I am going to summarize what we've covered heavily in class already, measures of variability, a complementary set of descriptive statistics that are usually reported along with measures of central tendency, which we just covered in the previous chapter. So you'll find all of this information in chapter 4, and you can also find the PowerPoint slides as a standalone download in D2L. Lots of information in the notes section of the slides for those of you who may be struggling or have some questions about some of the solutions. In this video, I'm going to heavily focus on the conceptual aspect of measuring variability. Underneath this video, you will see video links to direct problem demonstrations walking you step by step through the computations required to calculate the various measures of variability. So if you're having trouble with the computations or the math, I'm going to encourage you to check out those video solutions that are directly listed below this video. Okay, but for now, let's go ahead and get started. When we talk about variability, we're talking about distance. Okay, how different or how far away are scores from one another in a data set or in a sample? Are scores really clustered together? Are people reacting, behaving, or performing similarly on a test or an assessment? Or do we see a lot more spread in the results? Are people kind of falling all over the place? So you can think of variability as just a fancy word for differences. When things are variable, it means they're not the same. In statistics, one of our goals is to measure the amount of variability for a sample of scores in a distribution. To put it really simply, if the scores in a distribution are all exactly the same, then there is no variability. If there are small differences between the scores, then the variability is considered small. And if there are large differences and gaps between scores, then we're going to have a large amount of variability. So measures of variability are going to help us describe our distribution, and importantly, they're going to give us an indication of how well any one individual score represents the rest of the distribution. When variability is low, you're more likely to sample or capture a representative individual of that group than when variability is high. There's basically a lot more potential outcomes in terms of sampling people. Okay, we'll look at that here in just a moment. For now, let's turn our attention to two different populations that have an inherent difference in their variability. Over here, you can see a distribution for male adult height. Whoops. Okay, this distribution is reflecting men's height in inches. Okay, over here on the right, you can see men's weight in pounds. This distribution over here is by nature less variable. Notice that the mean height is 70 inches. And notice on the weight over here, the mean weight is 170. However, height is clustered much more closely together towards the mean than weight, which is much more variable. For instance, over here in terms of height, most heights are clustered together within 5 or 6 inches of the mean. On the other hand, weight is spread over a much wider range. It's not unusual in this distribution to find people who are more than 30 or 40 pounds away from the mean. Okay, so this distribution here for height has less variability, less gap or spread in the data than the distribution for adult weight. So variability describes the distribution. It's going to tell us whether scores are clustered close together or whether they're spread out over a larger distance. We're talking about distance when we talk about variability. Variability also tells us how much error we can expect between the sample and the population. In most of our research, we're using samples to ask questions about population. Okay, so when we have really variable distributions like this, our chance of getting a representative individual who falls close to the mean is lower. Okay, we could get somebody out here or out here, than when we sample from a distribution that has less variability. So for now, a key point is that variability tells us how much error to expect between the sample and the population. When you have a more variable sample or distribution, you can expect potentially more error than when you have a lower amount of variability. Now, there are three measures of variability that we've talked about. The range is a very crude measure. It's the distance covered by scores in the distribution from the largest score to the lowest score. Okay, so for instance, the range on exam 1 was between a score of 20 and 100%, okay, an 80-point range. This kind of measure is easy to calculate, but it's kind of crude and imprecise. It's only based on 2 scores, and it doesn't give us any kind of indication of how everybody else within that range has performed. As a result, you don't see it used as the high standard for reporting variability. Instead, we're going to focus on the variance and the standard deviation. The variance is a necessary step in order to get the standard deviation, which is the most common and well-accepted measure of variability used in research today. Okay, so here's some information on the range. Okay, you can feel free to look at the slides if you want to go into that in more depth. Okay, the standard deviation is the most common and most important measure of variability. What is the standard deviation? Well, it's the standard or average distance from the mean. It's going to give us a description of whether the scores are clustered closely together around the mean or whether they're more widely scattered out. Now, the calculations for standard deviation differ depending on whether you're working with population data or sample data. Your formula sheet for chapters 1 through 4 contains all of the formulas organized very clearly depending on whether you're working with a population or a sample set of data. Now, variance is a necessary companion concept to standard deviation, but it's not the same concept. Okay, we're going to go ahead and we're going to walk through what we're talking about here. When we want to get the standard deviation, what are we basically asking? We want to see how different scores are from one another. Okay, the word deviation means distance. Okay, for every single person in the data set, you can imagine that we can calculate their deviation score. Let's imagine that on the first exam, the average grade is an 80%. Okay, the average for the group is 80%, but you scored a 90. Okay, your score deviates from the mean by positive 10 points. In contrast, if you scored a 70, your deviation score would be 10 points below the mean. Now, for everybody in the class, we can go through and calculate the deviation score for that individual. At the end, we can get the average deviation score. Okay, that is essentially what the standard deviation is. It's telling us the average distance in the sample or the population from the mean. Now, the slides are going to contain some more information on the background of the math and where the formulas come from. Okay, but for now, I want to introduce step 1 for calculating standard deviation. Okay, getting the standard deviation requires a couple of computations. And the first is the sum of squares. Okay, you need to calculate the sum of the squared deviations from the mean. Now, what is the sum of squares? It's basically the sum of all of the deviation scores squared. Okay, now this can be a very time-consuming approach here using the definitional formula, because if you have 20 or 30 scores, that would require you to compute deviations for each one of those people. So the definitional formula is great for reminding us conceptually about what we're capturing here. Okay, we're getting the sum of all of the deviations in the group, but when we actually compute this, we're going to want to use the computational or the raw score formula. It's way easier, it's quicker, and it's less susceptible to human error. When we use the computational raw score formula, we don't have to calculate any deviation scores. We can plug the raw data directly into the equation. Okay, this formula can be found on your formula sheet, And it's basically broken up into two chunks. Okay, the first part of the formula here asks you to square every single raw score, and then add that up. The second part of the equation asks you to add up the raw scores and then square that total and divide by n, the sample size. You'll be subtracting the second part of the formula from the first part of the formula. If you haven't already printed out the formula sheet, jot this formula down so that you can do the next practice problem with us. Okay, here we have the computational raw score formula. And go ahead and see if you can solve this problem right here. You have a set of data. Okay, each score represents one person's performance on a math test. See if you can calculate the sum of squares. Make sure that you're following the order of operations and make sure that you're entering the numbers into your calculator accurately. Feel free to pause the video here as you solve this problem. I'm going to go ahead and continue and walk through the solution. This slide breaks down how to solve sum of squares for the previous slide. To get the sum of x, we add up all of the raw scores and we get a total of 54. That's going to be plugged into this part of the equation right here, and we'll ultimately square that number. We also need to get the sum of all of the scores squared. So we square each score in the data set, and then we add up that total, which comes out to be 546, and will be the first part of our equation. Now we have 6 scores total, so our sample size is equal to 6. We end up with 546 minus 54 squared over 6. This ends up being equivalent to 546 minus 486, and we get a sum of squares of 60. You need the sum of squares value in order to go on and compute the variance, which will ultimately allow you to get the standard deviation. You can use whichever formula you want, but I always recommend that you use the computational or the raw score formula. It's much easier, it's much more efficient, and it's less likely to lead to a mistake. Okay, in the slides, you'll find various practice problems if you want to go ahead and practice computing sum of squares. Feel free to download the PowerPoints. You'll find all of the solutions in the notes section. But for the sake of time and expediting this video, I'm going to go ahead and move into what do we do once we have the sum of squares. Now, please note that the sum of squares is calculated equally for populations as well as samples. However, when we need to calculate the variance, that's where there's going to be a slight distinction in the formulas. Here is how we calculate population variance. Once we have the sum of squares, we just divide by the sample size. So in the previous example, we would have 60 over a denominator of 6. Our variance would be 10 using the sum of squares and the sample size. In order to get the standard deviation, we just take the square root of the variance. So the square root of 10 would give you your variance. Okay, so these formulas are on your formula sheet. Essentially, once you have sum of squares, variance and standard deviation are really quite easy. The reason that we have to transform variance into standard deviation is because if you'll remember all the way in the beginning, when we calculated sum of squares, we squared all of our numbers. We want to unsquare it now to bring it back into normal units that people can understand and make sense of. Okay, I want to go ahead here and just jump ahead to what makes it different for samples. Okay, when you're calculating variance and standard deviation for a sample, the only difference is that the denominator has this n-1 adjustment. Okay, instead of previously with the population where we divided by the entire sample size, for samples, we take the sample size -1. Okay, so the variance for a sample is equal to the sum of squares over n-1, and in order to get the standard deviation, we just take the square root of the variance. Okay, so make sure that if you have a sample of data, you're making that adjustment in the denominator, you're using that n-1 adjustment. Why do we do this? Well, the reason is that samples underestimate the true variability present in the population. Here you can see the entire population. If we just sample 10 or 15 of these individuals, we might be led to believe there's less variability inherent in the distribution than really exists. By dividing with this correction, it reduces our denominator, and it's going to inflate the variance in the standard deviation slightly to serve as a correction for that initial underestimate. Okay, so here's an example from the sum of squares we calculated for 60. If it was a sample, we would divide 60 by 6 minus 1. That would be 6 over 5, and that would give us 12. We take the square root of that, and our standard deviation would be equal to 3.46. This means that on average, in this distribution, scores differ by about 3.46 points. The standard or average difference or spread among scores is almost 3.5 points. Okay. I want to go ahead and show you. Here we have some different graphs showing us how we can plot means and standard deviations. We did an example like this in class the other day. Here we have a frequency graph, and you can see the mean is 16. And standard deviation is equal to 2. Okay, we typically have arrows pointing out of each side of the mean, 2 points. Okay, this is giving you a description not only visually of the data and their frequency, but also of the central tendency of the data and the variability of the data. Okay, here we have the same thing for a population curve. Okay, for the population, the mean is 80, and the standard deviation is 8. Okay, so populations are usually graphed in terms of smooth curves. Here we have sample data. You'll also remember that for populations, we see Greek lettering. For samples, we do not see the Greek lettering. Another example here of sample data. The mean of this data is 36, and the standard deviation is 4 points. Okay, so if you get a question where you're being asked to graph the data and then also note the mean and the standard deviation in that data, you'd be doing something just like this. Okay. I want to go ahead and wrap up this lecture video with a really important conceptual point. Why do we care about variability in our studies? We care big time because variability has a huge influence on our ability to detect meaningful patterns in our data. The goal of inferential statistics, which we're going to get to shortly, is to find patterns and results in our data. The amount of variability present in the data influences how easy it is to pick up on these patterns. To kind of summarize this, you should know that high variability is going to obscure patterns, making it more difficult for you to identify trends and form conclusions. Sometimes we even call variability error variance. It's noise, and if there's too much of it, it can have a negative impact on our ability to get significant statistical outcomes. Here's an example just showing this point. Here we have data from an experiment, experiment A, and we have 2 samples of individuals. These individuals have been diagnosed with clinical depression. Sample 1 is in a control group. They're not receiving any active form of treatment, at least not yet. Sample 2 is exposed to a 6-week therapy program that is expected to improve mood in people with clinical depression. Down here, you can see the results of the study after the 6-week-long treatment program. Sample 2, their mood score, you can find the results up here. And for sample 1, the mood scores can be found down here. Now, within each one of these samples, there's low variability. Everybody in sample 1 is pretty much performing the same. And in sample 2, the individuals are pretty much reacting similarly to the treatment. Their mood is all consistently higher than that of sample 1. These data may lead you to say, it looks like this treatment is effective. Everybody in sample 2 had a higher mood score at the end of the research than in sample 1. It looks like this treatment produces predictable, consistent, and stable effects across people. However, the data over here from the same experiment show a very different amount of variability in the samples. By looking at this data, you cannot tell if the treatment is effective or not because the treatment is not exerting a consistent effect on all of the participants in the sample. We have people from sample 2 with lower, the same, and higher mood scores than people not receiving any treatment at all. To put it really simply, this data is really noisy and chaotic, and it's not easy to determine what's going on. In this scenario here, sample 1 has high variability as well as sample 2. People are scattered out all over. We will be coming back to this throughout the semester. In your research, you want to try to keep your variability low. Again, too much noise and variability in the data obscures your ability to form clean conclusions. This is one of the reasons why experiments are run very precisely in a standardized way. Everybody is kind of treated the same. There's a very strict process for running experiments to reduce noise and bias. Why are they doing that? They're doing that to reduce variability in the data. So this is going to wrap up my lecture overview on variability. This is a textbook chapter that you absolutely must read. These concepts will be at play throughout the rest of the course. And again, if you're having trouble computing sum of squares, variance, or standard deviation, please check out the videos underneath this video that are going to walk through the concepts showing you the calculations by hand. Okay, thanks, and I will see everybody soon.